Okay, guys, let's try to prepare for the paper three together. Okay, so before we jump into the paper three, I want to remind you the best tactic to prepare for IB exam. Okay, so table of content is I wanted to show you the last minute revision on my YouTube channel, what usually works, and what is the most essential part to prepare for the exam. So yes, you should definitely watch my video. Okay, thank you. But yes, if you look at the similarity index for this exam and our revision video, it's 100%, because the sys of Lin 3 was on the, I believe, paper one in Asia. And also you guys had to find the, what is it, domain and range of the composite function. I believe you had to find the range of something like a vertex form, wasn't it? Something like that, right? Not only just the domain, but also the range. Okay. And also, yes, you had to work with the homogeneous equation of a differential equation, where it would have been nicer to realize that we should have divided by x, no problem. Okay. And yes, I think there were a lot of vector problems in this year. And one of the questions in the paper too were to do with the kinematics, where it was very important for you to be able to find the velocity vector. And for that, we always have to keep in mind for the velocity vector, we need to be able to distinguish the speed, which is the magnitude, and then the unit vector. But anyways, I'm not trying to go over the paper one and two. It's a pointless. It's already a done job. And what's coming up is paper three. Oh, yes, another question, right? If you look at this, another complex number revision video, we went over this practice in February, and as you can see, the exact same question appeared. So it's very important that you regularly check the revision video before any test. Oh, yes, there's another induction problem, I believe, right? As you can see, this was the induction problem in the paper one, I believe, if we saw the video, could have been easily solved, easy peasy, lemon squeezy. And also another killer problem and the another very challenging problem on the paper one was something with the reduction formula, where you had to do a lot of integration by parts and then derive the recurrence relation. Was, as you can see, can be seen in our revision video. Okay, and and how did I know all this? There's no secret to this. All the answers are in the books. Okay, so if you look at these two questions from the Cambridge Press, now became hotter, right? One of the main example was to find the complex form of the cis form of 3 to the power of I. As you can see, that was one of the exam question. And also, if you look at this nice induction problem, this proof of this inequality using the induction was already seen in the book. So again, over and over, what I'm trying to emphasize is it's pointless to prepare the exam with the past papers because it's already a done job. You should really look for the essential questions on the books. Right? There are many amazing books, such as Hayes, Oxford, Pearson, and Hodder. It used to be Cambridge, but they always contain these beautiful, beautiful questions. And for your remaining time of a paper three, to prepare for the paper three, the best way to do is really attempt those paper three problems on the textbook. So what I want to go over in our gym session is to attempt those essential problems on each textbook, but not every question because we got no time for that. But something that you can definitely do on your own, and something that we can try to do together. Let's review them and try to see any questions that can be predicted. Okay. And of course, there's an IBO example question on paper three, which had this question that was identical for your section B problem in paper one in time zone in Asia. But yeah, that will be the our preparation for this time. So let's now delve into the realm of the paper three problems on textbooks. Let's get to it. So it's important for you to enjoy those problems, okay? So let's have a look at the first question from the Oxford, because it really, while going through the question, it really teaches you how to prepare for paper three. So what you need to do with the paper three is you need to always get the sort of gist. We always have to get the picture of what the question is by plugging some numbers, right? So what they are saying here is evaluate these the combination identities. No problem. We have done that. Okay, so we can evaluate those binomial coefficient, which is going to be, let's say this is a 1, this is n, this is 6 choose 5 over 2, which is the same as 6 choose 5 over 2, 6 choose 2 for the second one, right? So it's just they usually ask you to evaluate things because they want you to play around with the new idea and then extend from there, right? So here, what they are saying here is, as you can see, they ask you to check your insight. I think that's a very important comment from the textbook. It says for paper 3, what's going to be challenging is that you're going to have a new idea, unseen problems, and they usually give you steps to try. Okay, so what they are asking, state what property of Pascal triangle you answer to the I and explains. So for D1, okay, they just simply ask you to prove it, and what you can do is to prove using the left hand side and then the right hand side, right? So we have a left hand side identity as well as the right hand side identity. So what I can do is whenever you're proving, I can start with the left hand side, which is going to be n choose n minus r, which is going to be n factorial over, and then we subtract n minus r factorial times n minus r factorial, which is same as n factorial over r factorial times n minus r factorial. That's what we have. So that's okay. But also I can show the right hand side of the n choose r, which is going to be same as this. And I use the definition again. Okay. So from here, what you realize is that they are the same because of the multiplication as a commutative property. Changing the order doesn't change the value, right? So you're going to say, well, they are the same by commutative property. And also, not only do we show that the algebraic part, you also have to give your insight. You also have to give your insight, such as what can we apply that on the Pascal's triangle? Oops. They're going to ask you how you can try that on the Pascal's triangle. So can anyone please type on the chat what property I can apply on the Pascal's triangle from this binomial coefficient? You can write me on Zoom chat. Yes, very good. It is symmetrical, right? Very good. Right. So those things we have to observe and then answer. So that's great. What they often ask you to do is also play around with numbers. In this case, they ask me to add 2 consecutive terms on the Pascal's triangle. And then upon that addition, they also follow up with an identity in the next row. And then they will probably ask you to compare. And the reason doing so is because this induces something called the Pascal's identity. That's another observation we can make on the Pascal's triangle. When we have 2 entries in a row, such as 5 choose 2, 5 choose 3, if you add, you move on to the next row. And then that's going to be same as the 6 choose 3. So they ask you to, for example, to observe a symmetric behavior of the Pascal's triangle, as well as when we add, I'm going to move on to the next row, right? So that observation as well as the algebraic proof is necessary for this problem. And I think this is a great example the textbook can show you because they always try to tell you to use the clue from the previous part. That's super important. And since the permutation combination problem wasn't seen in time zone in Asia, I think playing around with the binomial coefficient can be a thing for this upcoming test. And another thing that I want you to remember is something called a hockey stick theorem. So for the Pascal's triangle, there are many things, but among them, I think what could be potential question is again Pascal's identity, and then also the hockey stick theorem, which I have prepared for as a question. So we will go over in a meantime. But that's the spirit. We always have to gain some insight from the previous question. That's great. And also, they ask you to evaluate some series on the binomial coefficient. Okay. And for paper 3, what I want to remind you is you're more than welcome to use a calculator. So we should know how to evaluate things very quickly. Okay. So what we want to do is you want to make sure to evaluate those values on your calculator. So I'm going to go to the Inspire, and we should know how to evaluate things quickly. So what I would do is press menu, and then we are going to do the summation, and I'm going to go for n equal to 0, okay, to 3, And then what you can do for the combination, you can literally type NCR and then 3 comma n, right? If you do that, I found that value. And what I can do is maybe I can do the summation of and choose n equal to 0 to 4 of NCR and then 4 comma n, right? So if I do that, I get 16, right? So I see this pattern, this is something similar that you had seen on the previous paper 3 problem, which was something with the gamma function with the n factorial. So playing around with the calculator and being able to find the pattern is also important. So what do you think the value is going to be if it was a 5 before even plug it into the calculator? That you should be able to tell. You shouldn't get your insight after having computed it. With the previous two information, what do you think the next value is going to be? We had 8 and 16. What do you think the next one is going to be? Anyone can give me an insight in the Zoom chat? I'll be very happy to. So we had 8 and 16. And now this time, yes, it can be an arithmetic sequence of a common difference of 8, maybe. And I give my insight and I confirm this on the calculator, then boom, I got 32. Then you realize, it is not arithmetic, it may be geometric, right? So then what you can realize, using the calculator, I could gain my insight, I can correct my initial intuition. This time, I realize that this is going to be something to the power of something of a geometric sequence of the common ratio of 2. Hence, this becomes 2 to the power of n. That is a great, okay? But you obviously have to prove it. And in order to prove, what the question has asked you to do is to use a binomial expansion. That is actually great. And for the something to do with the binomial coefficient, Pascal's triangle, the best binomial expansion form is often 1 plus x to the power of n, right? And if I expand here, I get n choose 0 plus n choose 1 x, n choose 2 x squared, goes on and on and on. Then it's going to be n choose n times x to the power of n. That is a beautiful, okay? And now, in order to get the sum of these binomial coefficient, what I'm going to do is replace the x value to be 1, right? If I did, then you realize the values are going to be just a sum of all the binomial coefficient from r equal to 0 to n choose n, and that becomes 2 to the power of n, and that confirms my insight. So even if you gained the insight, okay, you still have to confirm algebraically. So one of those paper 3 problems often mixed with the use of calculator. So please be able to use it fast, and also be able to sort of reassure with your initial insight. That is great. Okay. So if I look at for the J, that's another binomial coefficient identity that we often see in the exam, right? There was once something to do with the binomial distribution and this deriving this coefficient. So, but this time they ask you to use a binomial expansion. So that is a great, okay. How would you guys be able to initiate this problem? What would be the first line of equation? You can start by investigating the 1 plus x to the power of 2n and be able to come up with this binomial coefficient. How would you start the problem? So please, anyone, you can write me a Zoom chat. Oh, I'd like to start with this. I'd like to start with that. Would be amazing. Because very likely the questions wouldn't tell you how to do. But instead, this time I need to be able to come up with the method based on what I've been practicing. Yeah, very good. It is going to be a binomial expansion, but here's the thing, we have equality. That means you're going to expand in a different way, but still aiming for the same result. Okay, so what I mean by that is if I start expanding right away from here, and then I need to see whose binomial coefficient I want. Do you want the binomial coefficient of x squared, x cubic, x10? Whose binomial coefficient do you want in this time? What power of x do you think I'm looking for? For this time, I'm not looking for 0. I am not looking for the independent term. Second last, no, second last will be x to the power 2n minus 1. And for this identity that I have to observe, would probably have then the binomial coefficient of 2n choose 2n minus 1. And that is not what I'm interested in. In fact, it needs to be the term in the middle. And therefore, what I want is the coefficient of x to the power of n. That is great. That I had to see. That I had to see from the result that I had to show. Because why? We had out of 20 many terms, I'm choosing n many terms. So that's going to be the one in the middle. So from here, I don't have to expand all that, but I do know for the coefficient of x to the power of n will be simply 2n, choose n. So that's going to be the one representing on the left-hand side. And how can I then compare this expression to the right-hand side? What modification would you make in this 1 plus x to the power of 2n? I gotta change the form. How would you change the form? Pascal's identity? No. Here, if we were to use Pascal's identity, that would have been humongous. That would have been a humongous expansion. Yes, I think that second step is very important, isn't it? Because I know what I can do with the left-hand side because that's a simplified form. But to get to the result, what extra line of a deductive thinking do I need to put is the key for especially paper 3, because you always have to find a clue. And this time what you can do is to break this down, all right, into the power of n. What I mean by that is I have a 1 plus x to the power of n times 1 plus x to the power of n. That's what I would do, right? So that breaking into this product of term is key to succeed in paper 3 because no one is telling us. And from here, our job is to get the, what is it? The coefficient of x to the power of n. And for that, there will be quite a few terms, right? Because each term will be expanded out by the following. It's going to be n choose 0 plus n choose 1 x, n choose 2 x squared goes on and on and on. And I'm going to have n choose n x to the power of n. And I'm going to repeat this process again. That's great. But I'm not obviously interested in expanding this series and have, for example, how many terms would you have? You know, I would have n plus 1 square many terms. I'm not interested in that. I'm only interested in the expansion to achieve the coefficient of x to the power of n. Okay? So if I were to pair this n choose 0, should be paired with the n choose n with the x to the power of n. So it's going to be the product of n choose 0, n choose n, x to the power of n. Very good. Plus, what about this term here? N choose 1. That should be paired with who? N choose 1 times x should be paired with which term on the second expansion? Yes, n minus 1. Very good. So I have a n choose 1, n choose n minus 1, and it's going to have the same term of x to the power of n. And we can continue this on and on and on up to the n choose n times n choose 0 x to the power of n. That is a great. And with this, you realize, this will also be used with the identity that we proved that the n choose r is the same as n choose n minus r with the symmetric property of a Pascal's triangle. So I can actually change everything into the perfect square form. And that is the importance of that problem. What is important about this problem is that when they ask you to prove something, maybe one side is probably easy to start with, but being able to break this down into the two terms and then compare with the same coefficient is not stated in the question. We have to come up with, and that is the deductive thinking that you need to practice on until the very last minute prior to the paper 3 question. So this is a lovely problem from the Oxford book. Okay, so let's move on to the next question. So because this example really tells you what thinking we have to give, right? And then, you know, for this problem, we were using a lot of calculator, especially we were using calculator on the sigma identity. So now, while, you know, before I go further with the questions from the Oxford, I want to show you one mock test problem from a certified IB examiner, and he gave a prediction paper. And in this question, you know, I'm not keen on going over everything, but I do want to talk about part E. Okay, part E. This question I want to talk about because this is something that many people skip learning. This is the parametric equation of a question. So for that one, you know, let me just quickly open up another paper 3 problem that was important with the calculator. Give me 1 second. Yeah. In this question, it was about the hyperbolic cosine and hyperbolic sine and how it can be used with the complex number. Beautiful, beautiful problem. But what I want to have a look at is this, right? In the question, okay, they have given you an equation. They've given you an equation of, for example, they've given you an equation of a circle. They've given you this equation of a circle with the x squared plus y squared is equal to 1, okay? And that is a Cartesian equation of a circle. And then this is a parametric equation of a circle. And we should be able to use vice versa because the question has given us, right? This is not in the syllabus, but since they have given me what it is, I should be able to use it, okay? So for example, if you were to sketch x squared plus y squared equal to 1 on the calculator, you cannot do that directly because on the calculator for the graph, for the inspire, you can only do so if y is subject, right? So if y were to be plus minus square root of 1 minus x squared, then you can graph that. However, there's another way you can sketch, even if it's test mode, is to use the parametric form. So I want everyone, please take out your calculator, okay, and then go to the graph, all right, and then press menu, okay, press menu, and then go to the graph entry, okay. And here there are many options in my calculator, but then I'm not on test mode. On your calculator, if it's test mode, you will be only seeing 3 options, namely the function, sequence, and parametric. So here I'm going to use a parametric. In the x coordinate, I'm going to put cosine t because in the question they have given me my x value is cosine t. For my y coordinate, I'm going to put sine t, right? And as you can see, if I do the zoom fit, I see a circle, right? And that is a wonderful way to graph. And so what I wanted to show is that you should be able to display the parametric equation on the calculator because it's available even on the test mode. So that is great. But my question, I'm going to ask 2 questions. So on this November, I don't know what year, I think it was November 2021, they have asked me to sketch the hyperbola. You can do so maybe by taking the y, okay, as a subject. So it's going to be y plus minus square root of x squared plus 1. That could have been a way to sketch, but it's not welcome, right? It would be a lot nicer if you knew how to sketch using the parametric equation, okay? So check this out. So please pay attention. The parametric equation of a circle on the exam question, on the paper 3, was given to be cosine and sine, okay? And now you have to come up with another parametric equation of the hyperbola. What function can you assign on your x and y for the hyperbola is my question to you. So anyone please willing to do this, send me a Zoom chat. I will answer you. For this one, unfortunately, if I do cosine and sine, I don't get the 1, right? If I put the cosine and sine here, I get the cosine square minus sine square, which is not always 1. That's just a doubling of cosine. So the substitution with the cosine sine or different sign wouldn't give us the expression. So make sure you're trying on the piece of paper or on your iPad because it's very important to put yourself in the exam situation, right? As you can see, this was the exam question. We should know, or we should at least try to put ourselves under pressure. Do not rely on my answer. When I ask you to solve it, try to sweat, all right? And then try to make some gibberish in the paper and try to come up with some answer. Because again, paper 3, you will be so shocked how times can fly. You will run out of time. So it's important to be exposed to the pressure constantly. So here, what other functions can you give for the cosine sine? Very good. So what was important here is for the circle, we gave the trig identity. Right, we gave a trig identity of a Pythagorean identity of a cosine square plus sine square is equal to 1. And maybe we can do the same thing for the hyperbola. And this time the cosine sine didn't work, but yes, secant theta, tangent theta would work because 1 plus tangent square is equal to secant square. That we had to be able to see, okay? So if I change my zoom, maybe I will do the zoom standard and onto this equation, I'm going to put this secant and tangent. But on the calculator, my parameter was given t instead of theta, so make sure you put t. So I'm going to put tangent t here also, then boom, I do get the hyperbola. And thankfully, if you use a parametric equation, you also get the slanted asymptote. But unfortunately, on the calculator, it doesn't tell you, okay? On the calculator, it doesn't tell you what the gradient of the slanted asymptote, but can you please guess it? You can try on your calculator, or you can see my screen, but can you please guess what the asymptote, what's going to be the gradient of the asymptote? Yes, very good. Here, the slanted asymptote is actually going to be y is equal to plus minus x. And that we actually had to put on the answer, right? They ask us to not only sketch, but also indicate any asymptote. But if you were to sketch with the plus minus square root of x squared plus 1, you do not attain the asymptote, okay? So the reason I'm talking about this is this was one of the prediction question given by the IB examiner in a school. And then he asked us to, sorry, where is it? He asked us to sketch this, right? So for that one, you should be willing to, graph this on your calculator. So be able to know, please, how to use the parametric form. So I'm going to press menu. Oops, give me 1 second. Let me just change this into, yeah, that would be better. Here, let's put the menu and graph entry. I'm going to go to the parametric form. Let's try to plot this. You know, why not? So it's going to be 2 times t, right? And I have rational, sorry, 2 times t, oops, plus rational form sine 6 times x t. Unfortunately, I don't have much knowledge on the CG50. I think it's probably the best way to check is Googling it. I'm sure it will be available. I'm sure it will be available because every calculator pretty much allows you to use the parametric. No problem. And if I, oh, sorry, I was meant to put t, right, for the parameter. T. And then if you see the graph, you know, even if you don't see it, maybe you should try to zoom in or zoom out. Give me 1 second. Why doesn't it show? 2 times t. Oh, I got it. I think I got the order incorrect, isn't it? Because on the calculator, on the question, it says y. Oops. And then let me try again. X coordinate is t plus rational cosine 6 times t, and then the over t. Okay, good. And then for the y will be t plus cosine 6 times t over t. Yeah. So as you can see, oh, sorry. Y meant to be 2t. Why am I tripping? So it's going to be 2 times t and then the sign. Yeah. As you can see, you see the behavior like that, right? You see the behavior like that. And now using this observation, okay, the question says using this observation, all right, similar to what we saw in November 2021, okay, similar to that, they ask you to find the asymptote, right? They ask you to find the asymptote based on the observation we see on the question. What asymptote do you think you can make based on the graph we see? For this one, you cannot compute. You have to sort of yes, very good. I do have horizontal asymptote. Okay, I do have horizontal asymptote, but also you do have the slanted asymptote also. You actually have 2 asymptote. Well, I don't know why it's not taking a screenshot. Sorry. Let me see if I can take a screenshot here and then paste it on my iPad. Okay, whenever I have a problem with the iPad, let me just restart the iPad quickly and resume. But everyone, please try the parametric equation on your calculator also and see yourself if you get 2 type of asymptote also. And for those of you who don't hold the Nspire, please Google it. It's important that you're able to graph the equations on the special calculator. I'm restarting my iPad. Okay, give me 1 second. Hopefully it's gonna work this time. Okay, where's my graph? Yep, I believe it was this one. And if I take a screenshot, yes, a lot better. And then I'm gonna paste it here. Then boom, I get that. And please notice you will have the slanted asymptote, 1, and then the horizontal asymptote. That's another one, right? That's a great observation. But here's the thing then, what do you think the gradient of the slanted asymptote is going to be? What's gonna be the gradient of the slanted asymptote? Yeah, for the gradient, I'm gonna do the rise over run, isn't it? Okay. So for that, I have a y over x. And as you can see, for the gradient of a slanted asymptote, that's the end behavior as t goes to infinity. Okay. So what you realize that the gradient is going to be similar to 2. Therefore, I can make the, what is it? And if you ask me, how do I know it is 2? Is that, I've got this rise over run, right, for the expression. What you can do is divide top and bottom by 2, right? If I do, I got the 2 plus sine 6t over t squared over 1 plus cosine 6t over, oh, sorry, if I divide top and bottom, oh, I am dividing top and bottom, that's great, that's a t squared, and they would converge to 0 as t goes to infinity, so that the gradient is going to be 2. So here you expect my slanted asymptote is going to be 2x. So being able to observe that on the graph is important. We don't see that right away if you are not to graph that is also another comment that I wanted to give. But let's continue on the, what is it? The questions on the paper 3. Here's the thing I want to tell you. Here's the thing I want to tell you. The reason I ask you to solve a lot of paper 3 problems from the textbook, okay, is because if you look at the question from the Oxford, right? If you look at the question number 1, the question they recommend you, okay, Vedant, what tower does it say? It says Hanoi Tower. And I want to remind you guys, this was November 2023 paper 3 problem. You can check yourself, okay? You can check yourself. So that was the, what is it? The paper 3 problem. So what I want to remind you is it's important for you to solve many meaningful questions from textbook. It's all hidden there. So let's have a look at the next question. But I'm not going to go over the Hanoi Tower because it was already seen in November 2024, and I want you to try yourself. Let's have a look at the question number 2. Okay, let's have a look at the question number 2 from the AA Oxford paper 3 preparation. Here it's going to be integral calculus. Okay, so what I think you can do first is maybe you can start with this integral. Okay, and I want to remind you guys, all right, how would you integrate this function? That means you need to start with whether it's going to be substitution or by parts. What do you think? 50-50. I want you to just tell me whether it's going to be substitution or by parts. Yes, it is going to be substitution. What substitution do you think we should make? Very good. Okay, very good. It is a tangent theorem, right? And then it has to be it has to come from your natural practice. Very good. So that's great. So I'm gonna start with the what is it? The x equal to tangent theta, no problem. Then number 2, I'm gonna go for the derivative. Theta, which is a secant squared theta, but yeah, it's actually okay to leave it as a secant squared theta, no problem. And number 3 is dx is equal to secant squared theta times d theta. So that's great. And now I need to change my integral with the different bounds and different expression. If I put x equal to 0, tangent should have a 0 angle. If I have x equal to 1, tangent should have pi over 4. Make sure you change your bounds, all right? And I have a 1 over square root of 1 plus x squared. That's 1 plus tangent squared. That's a secant squared. But if you put a square root on it, you get a secant, okay? And that is great. I've got the secant squared theta here also. It cancels out, okay? And then the expression I have is a 0 to pi over 4, and then the secant theta d theta. So this question, the journey of this problem, is to work with the integral of a secant theta. They're going to ask you to see how you can integrate the secant theta, giving you some identities. But of course, on the paper 3, they will give you an identity and ask you to prove it. Okay, so that's very interesting. So for example, I want to ask everybody, if I have a t is a tangent theta over 2, express. This will be paper 3 style proving identity problem before integrating this monstrous secant theta. I want to ask, express, okay, sine theta in terms of t. How would you do that? You don't have to solve everything. You can tell me, oh, I would do this, I would do that, is all I want to hear. Oh, I will start with this, I will start with that, is all I want to hear. For example, oh, I'm going to use Pythagorean identity or compound angle, who knows? But what would be your initial step? But please, if you know, send me a Zoom chat. I would say yes or no. And make sure you're putting yourself in a pressurizing environment. So there's a similar practice for the paper 3. Very good. Okay. Yeah. half, or in fact, the double angle. The reason what we can do here is I need to match the period, guys, all right? I need to match the period the same. If your trig equations or functions doesn't have the same period, it's very difficult to solve. So here, I'm going to go in the same frequency here. The sine 2 times theta over 2 is important for us to initiate because the question is not going to tell us. From here, I observe, aha, I can actually use the double angle. It's going to be 2 sine theta over 2 cosine theta over 2. That is great. But here's the thing. My job, all right, is to express in terms of tangent. I don't have a tangent, but it's okay because I can arbitrarily make one by, let's say, multiplying the cosine top and bottom. Doing so, I have sine over cosine here, which is going to be 2 tangent theta over 2. But on the next term, I've got the cosine square theta over 2, where you know the cosine square theta over 2 is in fact the same as 1 over secant square theta over 2, which becomes 1 over 1 plus tangent square theta over 2, which is going to be replaced by t. That is beautiful. So here, this identity now can be simplified as 2t over 1 plus t square using the double angle and Pythagorean identity. Very good. So that's one way to express sine in terms of the tangent half angle. Okay, so that's great. And we're going to use that. We're going to use that information on integrating the secant theta when you were given another substitution, t is equal to tangent theta over 2. But this time, I believe you need to describe this secant as a 1 over cosine. And I'm going to try to express cosine theta in terms of t, okay? Where you can use, double angle once again. So cosine 2 times theta over 2. And this time, maybe I'm going to use the double angle form of a cosine squared theta over 2 minus sine squared theta over 2. That is great. And what do you want to do? I want to make sure to factorize these first two terms by the cosine squared theta over 2. Why? Because everything to factorize or divide would usually give you a clue about the tangent. If you want to get cotangent, you would always factorize or divide by the sine. And in this time, if I do so, I get the 1 minus tangent squared theta over 2. Very good. So you get the 1 minus t squared over 1 plus t squared. So that is wonderful. Now I'm going to use that understanding for integrating the secant theta. Okay, so now let's start the journey here. So you just confirmed, okay, that the cosine theta is going to be expressed as a 1 minus t squared over 1 plus t squared. Okay, that's great. So now I'm going to go with integral. And because it's a reciprocal, I'm going to write the 1 plus t squared over 1 minus t squared. Okay, that is great. But now, who needs to be expressed? Who needs to be converted? The d theta must be converted into the t. So for that, I'm going to differentiate my initial substitution. So I'm going to do dt over d theta is equal to 1 over 2 secant squared theta over 2 by the chain rule. But again, the secant squared will be same as by using the Pythagorean identity, 1 plus t squared. Easy peasy, lemon squeezy. The d theta now will be 2 over 1 plus t squared dt. That is great. Now I will put that, okay, in the d theta. So as you can see beautifully, 1 plus t squared, 1 plus t squared simply just cancels out. And please be careful because 0 and pi before were for theta. I'm making, what is it? Different substitution now. I'm making different substitution now. So if my theta value were 0, my t value will be 0 indeed. But if my, theta value were pi over 4, my t value will be tangent pi over 8. No problemo. It's okay. We will evaluate that later on using maybe half angle. Don't worry. Now let's try to focus on integrating this. So now I have a 2 over 1 plus t squared. Let's actually try to focus on indefinite integral because it's more challenging actually because I want to bring it back in terms of x. So I will evaluate, don't worry, but let's try to with the indefinite integral first. So from here, how would you guys continue evaluating this integral? Because I haven't integrated yet. I just try to keep changing the form, but now what do I do? What do I do? From here, please tell me Send me a Zoom chat. Oh, from here, you should continue doing this and doing that is what I want to hear. Yes, I want to integrate, but how? I cannot integrate right away. Please tell me anyone. Please try on your paper because it's important that you're trying on the paper. Yes, you got to use a partial fraction. But here's the thing. You will use a partial fraction, but make sure you got to take out the negative. I will take out the negative there too. And it is actually important that you do this. You cannot just do the 1 minus t squared right away. Why? Because from here, I'm going to use the identity of a 1 over AB. It's the same as 1 over B minus A, 1 over A minus 1 over B. So that is correct. And doing so will get rid of the t, you see? But if I didn't have, what is it? If I didn't factorize by the -1, it doesn't get simplified that well. Okay, so that's great. So I have a -2, 1 over, and I'm going to use a difference of square, t minus 1, t plus 1, dt. Very good. So then I'm going to use this partial fraction identity. So no problem. I have -2. That is great. And if I do the b minus a, I get 2. That is beautiful. And I'm going to have a 1 over t minus 1, and then minus 1 over t plus 1. That is a great. Okay, that's excellent. So the 2 cancels out. Now I can multiply the negative inside. It's going to change the order. So it's going to be 1 over t plus 1 minus 1 over t minus 1 dt. And if you integrate, what do you get? I get the ln of absolute value of t plus 1 over t minus 1. Let's see. But here's the thing, I started with the indefinite integral because I want to show you guys that the job is not finished. Job is not finished because we have to bring it back, guys, all right, in terms of x. I have to bring it back in terms of x, where we made series. We made series of substitution. The secondary substitution was a t is equal to tangent of theta over 2. But we had the initial substitution was, I believe, x equal to tangent theta. Oh my God, right? So for the indefinite integral, I got to bring it back in terms of x. So what would you do? So if I put it back in terms of theta first, I got the ln of tangent theta over 2 plus 1 over tangent theta over 2 minus 1 plus c. But my job is put in terms of x. And for that, okay, what would be best way to start? From here, you got to do something to make into the form in terms of x more nicely. What would you do? Our mission now is put in terms of x. And in fact, the question on the textbook, okay, asks you to describe integral like this. Your final answer, okay, will be, I think it was so your final answer in terms of x will eventually become ln of x plus square root of 1 plus x squared, something like that. So we're taking that journey right now. But from here, there needs to be done something. What would that be? Yup. I hope you're trying on the paper. I hope you guys are trying on a piece of paper. Whenever you're dealing with the trick, okay, I don't like working with anything but sine or cosine. So my best advice, okay, when you're trying to simplify things, but it's overcomplicated, please introduce sine or cosine because it's often making things simpler to deal with the trick. So what I mean by that is I'm gonna change the tangent as a sine over cosine. But I don't like working with the rational form. So what you want to do here, all right, is to multiply by the cosine cosine theta over 2, then bottom. Let's do that. I then have sine theta over 2 plus cosine theta over 2 over the difference. That is great, okay? That is wonderful. But I still haven't done anything in terms of x. But it's a good start because we love dealing with the sine and cosine. But onto this, what else would you do? What else would you apply so that it's easier for me to work with the x? Because right now, it's not easy to work with the x because the period is different. Right now, it's a theta over 2, but I want to deal with the theta, okay? So what would you do in this question so that I can change the theta over 2 to theta? Sure, what you want to do, okay, very good, okay, well done, is first of all, you got to change the order in the denominator. That's very important. So here, I'm going to change the order of cosine theta over 2 minus sine theta over 2. Very good. And the reason I can do this is because, look, this is absolute value. So it doesn't matter if I put the negative there. The changing the order doesn't matter because I got absolute value. It's only interested in the difference. Okay. And the reason it's better to work with the cosine in the front is now I'm going to multiply by the conjugate. Okay, sort of a conjugate. I'm going to multiply by the cosine plus sine theta over 2, then bottom. And doing so, you get on the denominator, I got the difference of a square, which I get the cosine squared theta over 2, sine squared theta over 2. And on the numerator, it's going to be a perfect square. So I have a cosine squared plus sine squared plus 2 sine cosine. But now you see, well, the sum of squares is going to be a Pythagorean identity. It is just 1, okay? And then what about the denominator? Yeah, this reminds us the double angle. Very good. Okay, so what I mean by that is that it's going to be 1 plus sine twice of a theta over 2. So it's going to be just a theta over, and this is going to be also the double angle of cosine, so cosine theta. And then what I can do is I can do the long division. So it's going to be cosine theta plus tangent theta. Okay, so that's great. So now I can re-express this in terms of the following. Oh, sorry, it's a 1 over cosine. Should be secant theta, right? So in that case, inside here will now become, what is it? The secant theta plus tangent theta. And then the reason this is better is because you had the x is equal to tangent theta. And what is very convenient, the tangent x can be easily replaced by the x, no problem. But what else? The secant theta, guys, how would you guys convert that in terms of x? How would you guys convert the secant theta in terms of x? Yeah, you can use, again, the Pythagorean identity. 1 plus tangent square is equal to secant square theta. So secant theta will be square root of 1 plus tangent square theta. Therefore, it will be something in terms of x. Then we have ln of absolute value of x plus square root of who? 1 plus x squared plus c is what we have. Okay. So good job. So this is the second question from the Oxford textbook. Please make sure you try because the question number 1 was given in November 2024, paper 3. It's always nice to see. It's always nice to try the questions in advance so that we are exposed to more new questions. But this is also a nice problem here. Let's have a look. I want to find so they have given you the new function here, the hyperbolic sine, okay? And they ask you to derive the inverse hyperbolic sine, okay? So now the next question is, look at this. This is my hyperbolic sine function. The question has asked you to find the inverse function. How would you convert is my question. What will be the initiative starting from this to find the inverse function? Please try, anyone, and then send me your approach on the Zoom chat, and I will check. Yes, for the inverse function, what you want to do, very good, is to interchange x and y. That is great. So now I'm going to have x is equal to e to the power y minus e to the power negative y over 2. To find the inverse, I need to make sure the y has to be subject. So what I can do is I can multiply by 2, and I have e to the power y minus e to the power negative y. How would you guys now try to make the y as a subject? So from here, what will be the next step? Please tell me. Moshi. Anyone, please tell me. How would you try to make the y as subject? Of course, I cannot take the ln. I cannot take the ln here because sum and difference cannot come out from the log. I hope you guys are trying on the paper. Yeah, very good. You can multiply by the e to the power of y on both sides. Very good. Why? Because, e to the power of negative y is 1 over e to the power of y. And we don't like having the unknown in the bottom. So what you want to do is multiply by e to the power of y, left and right. If so, then I get 2x e to the power of y is equal to e to the power of 2y minus 1. Okay, that is great. Then I have a e to the power of 2i minus 2x e to the power of y minus 1 is equal to 0. And how would you solve it? Now it reminds me of a quadratic equation, isn't it? Therefore, e to the power y will be my subject here. So it's a x plus minus square root of x squared plus 1, right? Then I can take the log on both sides. So I'm going to have y is equal to ln of x plus minus square root of x squared plus 1. Of course, I cannot have a negative in the middle because that will give me the negative input for the log I don't want, okay? Therefore, I'm going to have inverse function to be exactly the ln of x plus square root of x squared plus 1. That is great. So that's, what is it? The general sort of a differentiation, the integration problem with the Oxford problem on the hyperbolic function. Let's move on. And let's take a look at some paper 3 problem from Hodder. It's always important for you guys to try the paper 3 problems on the textbook. So now I'm going to go for the Hodder. Okay, let's have a look. So here, yes, it's talking about the Fibonacci sequence. Okay, that is a great, all right. And this is the typical Fibonacci sequence that we know of, right? We keep adding the terms. So let's see how we can progress. Now, this is going to be the paper 3 problem from Hodder now. We already have done the 2 questions from the Oxford. That is a great. Now let's move on to Hodder. Okay, so can anyone please send me a message on the Zoom chat what the F3, 4, or 5 is going to be? Send me a message in Zoom chat, please. What's going to be the F3, F4, F5? Is anyone trying? Thank you. All right, so we have a first 2 terms here, 1, 1, and then the sequence says that you need to add these 2 consecutive terms, right? So it's going to give you 2, 3, 5, etc., etc. And by the way, I think it's also nice, it's also important for you to know how to put the sequence on the calculator, all right? So you go to graph, okay, add a new page and go to graph, please. Press menu and put sequence, sorry, graph entry and sequence is what I have. And for the, I believe, so this is my sequence Fn, all right? So consider U9n as Fn. So the Fibonacci sequence is a recurrence relation depending on the 2 preceding terms. So I'm going to put U9, all right, of n minus 1, all right, plus U9 of n minus 2, right? And I was given the initial terms of a 1 and 1, right? I have 2 initial conditions in this sequence. So then if I press enter, then boom, it's going to display the Fibonacci sequence on the calculator also. And what you can do is to check those progression on the table. All right. So if you go to the split screen table, as you can see, the calculator generates the sequence for you. So it's always nice to know how to check the value. So I had the 2, initial conditions here, and you keep adding. So 2, 3, 5, 8, 13 were the expected terms on the the Fibonacci sequence. So very good. So you can easily find the 10th term or 20th term thanks to the help of calculator. Okay, so that's great. I've got 8 done. Okay, and Dominic suggests 1 is the only Fibonacci number which is a perfect square. Use a counterexample to disprove this statement. Okay, so it's a counterexample problem, right? So that means to disprove, you only have to come up with an example of a perfect square number, just the 1, to claim to say the claim is incorrect. So what will be another perfect square number in the Fibonacci sequence to counter argue this? I want everyone to try, please, and tell me what you get. Wow, very good. Okay, great answer. You found it so quickly, but I want to also wait for the others and give them a chance to compute on their own. Very important, but well done. Yes, good job. It is 144. Which is a 12 square. Very good. Okay. So for part B, I think using the calculator is important, right? Because on the calculator, if I scroll down on the, table, split screen table, I see 144, which is a perfect square, then boom, I'm good to go, right? So please able to see the, the value on the calculator. Great job. All right, let's have a look at the induction here. Okay, so they say, oh, the sum of square for the Fibonacci sequence, it says it's going to be the product of the consecutive term. So for the induction, what's important for us to start? For the induction, it is important for us to start with the basic step. So make sure you always try to show the n equal to 1. If n equal to 1, my friend, I have f. So for that one, you need to show both sides, isn't it? So I'm going to go with the left-hand side. Okay. When n is equal to 1, it's going to be f1 squared, right? So for that, it was the initial condition was 1, so 1 square is simply just 1, no problem. Then I go to the right-hand side. On the right-hand side, I see it's going to be f1 times f2. That's also 1, happens to be the same. I'm happy. Okay, now let's go for n equal to k implies n equal to k plus 1. So what it means is that if I try to write down my induction hypothesis, for which I can use for free, right? If n is equal to k, I could use for free. So n equal to k here, k, no problem. That I can use for free. But for the induction problem, it's always nice to know the result. I'm not going to use the result, but it's good to know where I'm heading. So I'm going to go with the r is equal to 1 to k plus 1. That's my result that I need to show. Fi square is equal to fk plus 1, fk plus 2. So here, I cannot use this result, but it's good to know where I'm going to start. So would you guys start the left-hand side or the right-hand side? That I want you to tell me. I want you to tell me for this inductive hypothesis, sorry, for this result to prove, which side is better to work with. Would you start with the left or the right? You can write me on the gym chat. Yes, very good. I'm going to start with the left-hand side because it's easier to use the induction hypothesis because it's a series form. So I'm going to add up to, so this means I'm adding from the first term to the k plus 1th term. That means I'm going to add, all right, starting from, sorry, it was I, right? The index was I in the question. So I'm going to change to I. 1 to k, fi square. Well, actually, let me just write as a series. Why not? So it's going to be f1 square plus f2 square goes all the way up to fk square plus fk plus 1 square. That's great. And then I'm going to go up to the kth term, replace that with my induction hypothesis. And that induction hypothesis was the product of fk and fk plus 1. That is great. And that will be replaced by the induction hypothesis, but the last term has to be added together, okay? But now I got a common factor. Let's try to factorize. It's going to be fk plus 1. Then I'm going to have the quotient of fk plus fk plus 1. But it doesn't look like the result that I had to show, where the fk was Fibonacci sequence. So how would you guys convert this? My aim of this statement is to show it's going to be product of consecutive terms of a Fibonacci sequence. But I've got to this far, it doesn't look like the yellow box. But how can I convert this? This is what I have. But I want to simplify further using the Fibonacci sequence definition. What was the Fibonacci sequence definition? In order to, yes, very good. If I have a 2, all right, consecutive terms, you move on to the next term. So if I have a fk and fk plus 1 added together, it becomes fk plus 2. So I'm going to have fk plus 1 times fk plus 2. Very good, okay? But of course, please don't forget to write down the conclusion, right? So since we show n equal to 1 true and also n equal to k true implies n equal to k plus 1 true, by the principle of mathematical induction, the statement is true for all positive integer. So far, so good. So we solved the part C. So I got the A, B, C. Okay, that's great. And then for part D, it's super nice, I think. Part D is super nice because it tells you to use the perspective of a certain thing in paper 3 problem. So tell me, what would be your initiative for part D? Tell me what you want to do for part D. You don't have to solve it, but oh, I will use this and that is all I want to hear. Oh, for part D, I will use this and that is all I want to hear. For example, you can say, oh, I will use, differentiation, integration, whatever. I don't know. But for part D, what would be the logic to start the problem? Yes, we got to use calculator, right? To see this pattern, okay, I got to use calculator. But if you ask me, how do I use calculator? Yes, as we talked about, okay, you cannot graph a curve, but you can plot the terms on the sequence. I want to find the least value of k, okay, where the term is bigger than the order, okay? So on the list of the terms that we define on the Fibonacci sequence, what will be the least k where the term is bigger than or equal to the order? What will be the least value of k in this case? According to the list on the calculator, what will be the least value? Yes, good job, right? K is equal to 5. Okay, so on the it's important to use calculator. K is equal to 5. So therefore, when you're trying to, okay, prove the inductive statement, it's important for me to know the basic step. Here, the basic step is when k is equal to 5. So now I want to prove this by induction again, but for that, I need to show that the f5 is 5 and is indeed bigger than or equal to 5, so basic step works. And the second thing I want to move on is if n equal to k, I need to show then the statement will be true for n equal to k plus 1. Okay, let's try to do that. So the induction hypothesis is fk is bigger than or equal to k. And the result to prove is going to be fk plus 1 bigger than or equal to k plus 1. So that is my aim to prove. For that, it is important for you guys to know which side. Which side do you want to start? Do you want to start from the left or the right? For this inductive statement, which side do you want to start? 뭐지? Yes, good job. I got to start with the left because that's the place where I can use maybe, the induction hypothesis. But here's the thing, my induction hypothesis is fk. I cannot use fk plus 1 directly. How can I link the fk plus 1 with the fk? My induction hypothesis was true up to k. So I've got the fk plus 1, so you got to bring down the order. And how can I bring down the order? Yes, we can bring down the order using the Fibonacci sequence, because by the definition of Fibonacci sequence, okay, this is same as fk plus fk plus 1. That is great. And with that, fk will be naturally bigger than or equal to k by the induction hypothesis. No problem. But guys, what about the fk plus 1? Sorry, fk, well, oops, my bad, minus 1. And I use, guys, the induction hypothesis on the fk minus 1. I assume for k to be true. Can I use for k minus 1? Yes or no? Type me, please. Can I use fk minus 1 as induction hypothesis? Yes. Good job. It is also true. Why? Because for the induction is like the dominoes. If I assume the kth brick falls, then every brick before has fallen. But it's just the matter that I don't know whether the next term is going to fall or not. I don't know that. But anything before, you can apply the result. That means this is going to be the fk minus 1 will be bigger than or equal to k minus 1. So what we do have is fk plus 1 is bigger than or equal to 2k minus 1. All right, that is great. But now what we want to do is eventually show the result. Our result was k plus 1. And I wonder if this is bigger than or equal to k plus 1. So this first inequality came from the induction hypothesis. But the second inequality should come from our logic, right? Because if 2k minus 1 was less than k plus 1, then it suggests k is less than 2. But that is a contradiction because our statement was only true for k bigger than or equal to 5. So this inequality is true by the logic. Therefore, we can prove, f k plus 1 is bigger than or equal to k plus 1, okay? So we show the induction hypothesis implies the result to prove. But then again, it's actually a really great example to remind you, you should really attempt some questions on the book that were not seen before, because I hope you understand, I hope you guys realize this is very similar to your induction problem in the paper 1, right? I believe it was ln n is less than or equal to n. You had to show that, right, by induction. And this example is very similar to what you just did. But anyways, we show that in inequality also. Part D is also done. No problem. Part D is also done. Let's have a look at part E. Now they are saying, oh, hold on a second. I have a solution for my Fibonacci sequence, they are saying. They're saying I have a solution for my Fibonacci sequence. And if I go back to the previous, if I go back to the initial definition was given as this. So tell me what step you want to take for E. How would you start on part E? Very important for you to read, try on your paper, and tell me the answer. I mean, tell me your attempt. Oh, I would have done this, and if I did, I get this equation. Is all I want to hear. You don't have to solve it. But tell me your initial attempt. But while you're at it, let me quickly grab some water. Give me 1 second. I'm back. Anyone has attempted this and, oh, I will do this and do that? Can you guys please tell me the logic? I'm gonna move on unless anyone give me an attempt. Please tell me, oh, I've tried this. Yup. Very good. What we should do is simply just substitute. They are asking me to substitute this into the recursion. This is the recursion. This is the recurrence relation of a Fibonacci sequence. So why not? Let's try that, guys. Okay. So if I sub it in this alpha to the power of n on the Fibonacci sequence, I got the alpha to the power of n plus 2 is equal to alpha to the power of n plus alpha to the power of n plus 1. All right. And maybe I will rearrange to the left-hand side. And maybe I will factorize. So given that the alpha is non-zero, you can do is you can divide this by alpha to the power of n. That is great. If you did, I get alpha squared minus alpha minus 1 is equal to 0. That gives me the expression, nice expression of a quadratic equation for which I can try. So alpha is going to be 1 plus minus root 5 over 2, I believe. Yes. Yes. So those are the two possible values of alpha. So the difficult part of the paper 3 is that they don't tell you to use quadratic equation, for example. So we have to get it by realizing, oh, I should actually sub it in. And doing so, it doesn't look like a quadratic right away, but because I was given non-zero value, I can divide. Then I've got a quadratic. I can use a quadratic formula, no problem. Here's a part E. And then it's another show that problem. Let's check this out. Now they are saying, okay, show that given the alpha, which was just a radical conjugate, so I got the one with the positive and one with the negative. They are saying that it's two possible values of alpha, and I need to show whether it's going to satisfy the equation or not. Okay, I need to show that this one also satisfies the recurrence relation, where the recurrence relation was, I believe, this, the Fibonacci sequence. Okay, let's try to plug it in then, right? We're gonna substitute once again. So if I did, I'm gonna raise the power with the n plus 2. So I have a, what is it? A times alpha 1 to the power of n plus 2 plus b times alpha 2 to the power of n plus 2 is great. And I'm gonna replace for the other two terms on the right hand side. That's correct. Boom, boom. So it's gonna be just a 1 and 0. Okay. And guys, okay, I need to show whether this is true or not. So I cannot say it is equal to, right? So this is my left-hand side, okay? And this is my right-hand side. And upon the rearrangement or simplification, I want to essentially show that it works. So that I cannot use, okay? So in this case, would you guys like to attack on the left or right? Please type me on Zoom chat. Would you like to start with the left or right? Is my question. Yes, good job. I'm going to start with the right because it's messy. It's always easier to start with the nasty and go to the clean for math. So now I have the sum here, and then you can factorize by the common factor, which is a. Then I've got the alpha 1 to the power of n plus alpha 1 to the power of n plus 1. That's great. Plus b of alpha 2 to the power of n plus alpha 2 to the power of n plus 1. And in fact, you know what? These were the solution. Okay, these were the solution of this Fibonacci sequence, and they are supposed to work because they are the roots. What I mean by that is this sum of consecutive terms according to the Fibonacci sequence should give you the next power by the definition of the Fibonacci sequence. So this is going to be changed into a times alpha 1 to the power of n plus 2. Same thing for the b. It's going to be times alpha 2 to the power of n plus 2 by Fibonacci sequence. So that is the left-hand side. So I start with the right-hand side, and I land it back on the left-hand side. So that's a good way to prove it. So in this one, what was important? Being able to factorize is important, and also being able to see that this sum of consecutive exponent can be changed into the Fibonacci sequence. So that's great. That's great. So we have done part F also. So now they're saying, okay, get us the alpha in terms of n. So that means they're trying to convert into the explicit form. So if we go back to the question, what we had is we were given this recurrence relation, but I found this explicit form where the alpha 1 is 1 plus root 5 over 2. Alpha 2 is 1 minus root 5 over 2. But tell me, okay, on this explicit form, who is the enemy? Who do I still have to verify? What are the term or number that is not given yet for which I have to find? Who is it? Yes, very good. Very good. I don't have those coefficients. I got to find it. And of course, it's going to be simultaneous equation, isn't it? And for that, I do have the initial condition. Remember, my first and second term of the Fibonacci sequence was 1 and 1. Okay, so that is great. So I'm going to use these initial conditions on the explicit form to get those coefficients. Okay, so it's going to be F1, all right, is going to be A alpha 1 plus B alpha 2 is equal to 1. That is correct. And F2 is going to be A alpha 1 square, okay? B alpha 2 square is also 1. But here's the thing, you know, this is a really, really important realization. I'll be impressed if you know, for solving this simultaneous equation, remember the unknown parameter is A and B. Alpha 1 and alpha 2 are given, okay? But who is causing big trouble? Who is the enemy that I want to simplify in this simultaneous equation? I mean, you can solve it directly here, but what is causing a trouble? I want to find A and B, but there's a term that's causing a trouble for me to work this with difficulty right now. And what is that? Yes, especially very good, the square term. I don't like it, right? Because these were the linear. You can use calculator. That is a great answer. You could. But here's the thing. Maybe putting all these numbers in the calculator will take me even longer, because remember, I got to put alpha 1 as a 1 plus root 5 over 2 and 1 minus root 5 over 2 for the alpha 2. It will take more time. What I'm saying here is, remember, these were the roots. These were the roots of this quadratic equation. Where was it? These were the quadratic equation of this quadratic. What I'm saying here is, you can actually make things in a linear term right away. Because this perfect square was difficult to work with in the exam, I'll be thinking, I don't want that, because I got to square it, and squaring the 1 plus root 5 over 2 is ugly. But instead, I can do alpha square is equal to, in fact, 1 plus alpha. Because it was a root, it would work, and I can actually linearize it. Every time you're linearizing the equation, is always nicer. It's always nicer. So I have a 1 plus alpha, sorry, alpha 1, isn't it? And then the 1 plus alpha 2, because of this quadratic equation. That is beautiful. So, and then if I then expand, I get the A plus B, I believe, and then the same thing, right? If you expand, I get AB, I get the A alpha 1, B alpha 1. That is great. Is equal to 1. But we already know. What do we know, guys? That this is going to be simply just a 1. That is beautiful. So I got actually A plus B is equal to 0. That is great. So A is equal to negative B. Okay, A is equal to negative B. So if I were to use it on the maybe one of the equations back again, maybe I will use it on the first equation where B is going to be replaced by negative A. Then I can factorize by the A. Then I get the difference of the alpha 1 and alpha 2 is equal to 1. Therefore, A is simply just 1 over alpha 1 minus alpha 2, where they were the roots, weren't they? So if I let the alpha 1 as a, 1 plus root 5 over 2, then alpha 2 will be 1 minus root 5 over 2, right? Because they were conjugated from the quadratic formula. If you see the difference, I see that it's going to be root 5. So if you reciprocate, I got the 1 over root 5. That is beautiful. And if you get the A, thanks to the, linearizing substitution, I will get the B also automatically negative 1 over root 5. That is wonderful. So now if I go back to the explicit formula, then I can find the particular solution, right? This A and B will be factorized by, will be substituted by the 1 over root 5 and negative 1 over root 5. So it's going to be 1 over root 5 of the 1 plus root 5 over 2 to the power n minus 1 minus root 5 over 2 to the power n is going to be your particular solution. So that is great, right? That is, of course, yes, as you have mentioned, you could have done simultaneous equation solver in the calculator, but if you see that this square thing can be reduced, then doing this by hand is quicker. But of course, you know what? I do want to talk about it. In fact, using the calculator is important. So, but the one thing that I want you to remember, okay, on the Inspire, I know, okay, I'm going to use alpha 1 and alpha 2 quite often. Okay, so what you can do is I can put the 1 plus square root of 5 over 2. I'm going to store it on the nth bar, please know where the store is, okay? So I'm going to store this as maybe A. So whatever the number I put, if I put A again, it's going to come back to it. That's beautiful. And what I'm going to do is I'm going to now maybe put the negative as B. So if I put B again, I come back to the number. And why it's nicer to work with, because then I don't have to manually put 1 plus minus root 5 over 2 many times. I don't have to do that. So here I'm going to press menu 3 and then go for the linear equation and then 2 unknown variable. My unknown in this time are A and B capital letter. Alpha 1 and alpha 2 are known parameter, which I stored. So I'm going to put, what is it? A times X plus, B times Y is equal to 1. And I'm going to put this time A square times X plus B square times Y is equal to 1. And if I press enter, I really hope to see 1 over root 5 and then the negative 1 over root 5. But as you can see, I do not find the exact value because on the test mode for the calculator, it would only give you the approximation. So I don't have the perfect 1 over square root of 5, but I still get it anyhow. Very good. Okay, very good. But also remember how to store the numbers. Okay, that is great. So I found the particular solution of a Fibonacci sequence on the part G. That is great. Okay, so how would you do H? I want everyone please attempt using the particular solutions of the Fibonacci sequence, which we just got it. If I show you again, it was this that were the particular solution. Please try H. I want to hear some answer. So please try H. Let me know once you get the value. Yeah, what you can do is to use this form right away. Oh, very good. Yes, that's the correct answer. Really well done. If I have a f n plus 1, that's going to be 1 over root 5, all right? And of course, you can put this in the calculator, okay? But let's try to solve by hand. I have a 1 plus root 5 over 2 to the power of n plus 1 minus 1 minus root 5 over 2 to the power of n plus 1 is the next term, and I'm trying to divide this. And who cancels out? 1 over root 5 cancels out. And here's the thing. You know what, guys? I'm sending, all right, n to infinity. I'm sending n to infinity. In that case, all right, between first term and the second term, who goes to 0 is my question. Term number 1, term number 2, who will converge to 0 as n gets large? That you guys, you got to tell me. Please tell me. Yes. Yes, because 1 minus root 5 over 2 is, as we have seen on the calculator, I believe it was a negative, but still between 0 and 1. So if you put that as infinity, you know it is going to get 0. So is this one, okay? So you're only looking at the ratio of this. You're only looking at the ratio of this, where, if you divide by the n, it cancels out. You got the 1 plus root 5 over 2, and that's your golden ratio, okay? This is your golden ratio. Very good. So, and here's one more comment that I want to make for paper 3 problems is often it's unseen problems, but it's got the historical significance. Of course, for this problem, it's about the Fibonacci sequence, isn't it? About the recursive relation. And the last part is about the golden ratio. And for the previous question on the Oxford paper 3 problem is about the hyperbolic sine and hyperbolic cosine. So all the questions you usually have a historical significance. It's about Hanoi Tower, etc. etc. So please make sure we are expecting some of the historically significant field of mathematics. So let's have a look at another paper 3 problem from Hodder. Okay, right, that's great. So let's have a look at the guys of this. Okay, for part A, it's arithmetic series, okay, with the induction. I will leave it as an exercise. Please, I want you guys to try. No problem. But let's have a look at part B, okay? Let's have a look at part B. Here's the thing, you know what? It's okay. So for part B, I can use binomial expansion, isn't it? So it's going to be n cubic, 3n squared, 3n plus 1. And I'm subtracting by n cubic. So that is great. Then I have who? 3n squared plus 3n plus 1. Easy peasy, lemon squeezy. But here's the thing. Check this out. Check this out, guys. By considering two different ways of expressing, I think it's a typo. It's supposed to be, let me just, what it is? It's supposed to be r is equal to 1. Okay, so it says, by considering the two different ways of expressing, they asked me to find the sum of integer square. Okay, as you can see, of course, one way, all right, one way of getting this expression of a sum is going to be what we just did, right? We are just going to expand the cubes inside and just get the quadratic term. So if the first way, all right, guys, the first way of simplifying this is this is going to be expressed as sigma r is equal to 1 to n of, well, we already simplified before, but you know, the sigma is in terms of r of the index. So I'm gonna put 3r squared plus 3r plus 1. That's one way to simplify this series. But the question asks you to find two different ways. So what, guys, will be the second approach to express this difference of cube of a series? I want you to please tell me. Please, when you're trying the problem, do not look at my answer only. I want you to try. It's very important to try. As you know, exam pressure will be there for paper 3. It will be finished in the blink of an eye. It's very, very fastly done. Yes, very good. You're right. What you can do is you can simply just do the expand the sigma. Very good. I don't have to do fancy algebra. Very good. So now I'm just gonna expand the sigma here from the first term to the nth term. Let's start plugging the r equal to 1. I have, what is it? 2 cube minus 1 cube plus 3 cube minus 2 cube plus 4 cube minus 3 cube plus, it goes on and on and on. And then, you know what? I'm going to go for the last term also. It's going to be n plus 1 cube minus n cube. That is correct. But here, I want to see which terms are going to cancel out. So 2 cube cancels out with the 2 cube here. Very good. 3 cube cancels out with the 3 cube. I'm sure that 4 cube will somehow be canceled out too. And here's my question. The second term remained, all right? The -1, guys, remained. Which term do you think will remain at the end? Yes, the second last will remain because it has to be symmetric. This difference has to be symmetric. So second term is there. The first term of the series will be there too. It has to be symmetric. So now what I have here is n plus 1 cubic minus 1 cubic is another of this sigma. But they have asked us to consider two different ways. But what's difficult about the paper 3 is that I don't know how to start, because you know they didn't technically tell me to expand the sigma, but it is our will, our deduction to open up the question like that. And I'm going to compare with. Okay, I'm going to compare these two, because one way or the other it must be the same. And then what you can do is expand the sigma here. That's going to be sigma r is equal to 1 to n of a 3r squared. And I'm going to distribute the sigma. So it's going to be sigma r is equal to 1 to n of a 3r plus sigma r equal to 1 to n of a 1. Okay, on the right-hand side, I still have this difference of cube, no problem. If you expand the other side, isn't it easier? Right now, of this one, I'm not assuming that I know the sum of r squared. We're trying to prove it. So I cannot use the, what is it? This result here yet. So I need to only use the existing knowledge. That will be namely this number 1 and this number 2. And of course, we can use the sum of integers squared, but I cannot use it because the question asked me to show that. I cannot use the result. So then, how would you guys simplify number 1? What series is this? Is this arithmetic or geometric? Are you sure? It's a disguising, isn't it? Because it's R, it looks like a geometry, but it's arithmetic because inside is a linear, right? And for that, it's gonna be the arithmetic progression and hence the arithmetic series. So we have a n over 2, that's the number of terms over 2, and the first term is a 3, and then the last term is 3n. So the series here would be 3 over 2 n times n plus 1, no problem. And can you guys please tell me what would be the simplification of this? Well, it's a constant, isn't it? So that means I'm adding 1 n many times. Oh, sorry. And for that, that's just n times 1, simply just n. That is correct. So now, if I look at the left-hand side, what happens? The second term was using this arithmetic series, no problem. And then the last one is just adding n. That is great. So now my job is to rearrange. Okay, my job is to rearrange so that I can simplify for the expression of the sum of integers squared. So on the right-hand side, I've got this. I have a, what is it? Minus n minus 3 over 2 and n plus 1. And you may argue, then shouldn't we expand? Yes, you could, but the beauty of math is always about the factorization. I want to ask you guys, what will be the common factor to work with in this right-hand side? What common factor do you want to give is my first question. What common factor would you give, guys, in this question? I will wait. I want everyone please to try. And close. And unfortunately, it wouldn't be a good choice because it does not factorize these. Yes, very good. N plus 1 would be a good choice. If I try to go with the n plus 1, well, because, you know, if you look at the second and third term, I can factorize by the negative. Then I see, the common factor of n plus 1. That is great. Then I have n plus 1 squared minus 1 minus 3 over 2n. Okay, why not? Then I should put into the common denominator. Okay, then it's going to be 2 n plus 1 squared minus 2 minus 3n over 2. Okay, then I can expand. Let me try to expand on that one. So it's going to be n plus 1 times. If I expand, I got the 2n squared plus 4n plus 2 minus 3n. Okay, that's good. So it cancels out here. It cancels out here. Just n is what I have over 2. Okay, so that will give you then n plus 1. And if you've factorized by the common factor of n, then boom, I have 2n plus 1 over 2. That is sum of 3r squared. Then I can divide it by 3 on both sides. That will give you 6. And that is our desired result. Okay, so always, if they ask you to prove it, you cannot use the result. Okay, so that is great. So we have done from A, B, C. Okay, but here's a word of advice. Okay, and of course, question can extend. Okay, guys, question can extend. What I'm saying here is the question could have then show it could have extended as the following. They could have asked you r equal to 1 to n of r cubic is n squared n plus 1 squared over 4. They could ask you that. All right. For that, difference of who do you want to start? It's a very nice question to follow up. I just want to hear, we did the difference of cube for the sum of squares. Then I'm asking for the sum of cube, difference of what do you want to use? For the sum of cube, difference of what do you think I'm going to try? Yes, very good. The sum of quartic will be somehow to associate with the sum of our cubic. So it's, as you can see, our algorithm. So if you want to derive, for example, r to the power of m, then you need to start with the n plus 1 to the power of n plus 1 minus n to the power of m. So that's another exam tips. But this question doesn't extend there. It just lingers around with the sum of squares. But let's have a look at part B. Okay. Now, of course, I got to use the result. For the paper 3, it always has hence or follow-up questions. Let's go with part D. Okay. What they asked me to do is to sketch the versable with the quadratic. Let's do that. Let's try to sketch the quadratic here. Y is equal to x squared like that. Let me try to maybe sketch better parabola. Okay. Yes. Y is equal to x squared is what I have. And they ask you to put what sum? The right sum, because the y value will come from the right corner. Okay. So sorry, let me just try to put this as a t square, and then put the value that I'm heading to is the x. Okay. Then how many times is it asking me to split this up? It's asking me to split up with the n rectangles. So any rectangle that's gonna be described by this n split is gonna give you the same width. It's gonna give you the same width. This width is going to be n over the number of times that I'm splitting is n. That's gonna be my width. That's gonna be my unison width. Okay, that's great. And then imagine this is my rth rectangle. Okay, imagine this is my rth rectangle, and I want to find its area. For the area, I need width and length. The width I already have, which is x over n. That's not a problem. How can I find the length? To find the area of the rth rectangle, I want you guys to tell me how I can find the length. Yes, very good. I got to use the function. But here's the thing. I am going to plug it into the function value. But my question is, what x value do you want to use? What x value do I need to use to sub it into the function so that I get the length? Very good, very good. It's going to progress, all right, guys, by the arithmetic sequence. That is great answer. So I start with the initial term of a 0. And for the rth term, all right, for the rth rectangle, this will be from 0 to r many times of my common difference, which is x over n. So in fact, this rth term is going to be r times x over n. That I'm going to put on my function, okay? That will give you then the width was always the same times the length will be described by the function, which is rx over n. That is a square, sorry, because it's a function. So that is the rth rectangle. But how many of them do we have? Because I split up by n many times, I should have n many rectangles. So I'm going to add this rectangle n many times, starting from the first rectangle to the nth rectangle. And using the expression of the area, it's going to be sum of r equal to 1 to n of this following expression of the rectangle. And beauty of math is always about the simplification. Right now, my sigma depends on the r. Any other term can go outside, okay? So if I expand it out by the perfect square, it's going to be r squared times x squared over n squared. That is great. And then I'm going to take out all the terms with the r. All the remaining terms will just go out. It's going to have x cubic over n cubic, right? Good. Sigma of r equal to 1 to n of just r squared, okay? But what's so great about this is because from the telescopic cancellation and binomial expansion, we derive the sum of integer square. We can actually plug it in. I'm going to plug this as n times n plus 1 and 2n plus 1 over 6. That is great. But here's the thing, guys. Look at this. What I'm doing right now is an approximation. And as you can see, for the right sum, for the increasing function, is bigger. The gap is slightly bigger here, you see? Okay, so that is going to be my upper bound. That is going to be my upper bound. It's bigger than the actual area under the curve, for which we often use integration. So I'm going to use integration from 0 to x over t squared dx is what I had. That's my upper bound. Now I return to my next question, because it says you got to find the lower bound using what corner? The left corner. They want to use the left corner. For that, you need to sketch. You need to sketch. So now let's try to sketch, the rectangles using the left sum. So I'm going to come from the left corner, which is for the increasing function, it's going to be lower bound. But here's the thing, you got to be very careful. You got to be actually very precise. All right, you got to be precise. What I mean by that is, as you can see, the rectangle that we started with, okay, was from A1 to AN, okay? And for the AN, I had the nth coordinate, okay? But if you look at the left sum, okay, I don't use the last term. I use the term before, okay? So that would have been xn minus 1, okay? But here's the thing. Number of times I split it up is the same. Both would have the same number of rectangles. I have n many rectangles here. I had n many rectangles here, okay? But just the terminal point is the different, because for the left sum, I got to use the coordinate on the left. Okay, so the series that I had before was r equal to 1 to n, thanks to the terminal point of xn, so that I guarantee n many. But if you look at the left sum, okay, my terminal point will be n minus 1th term, okay? But I still have to have n many. So my question is, what's going to be the starting point here? For my index here, where do I need to start is my question. Yes, very good. I got to start from 0. Thank you. So I got to start from 0. Still guaranteeing the n many is important, okay? Okay, so on that case, then all the expression is the same. The expression that we had about the rectangle is going to be the same. It's just that we don't have the same number of terms. So that's great. And then this is going to be same as what is it? Sigma. Well, but it starts from 0th term to the n-1th term, and the way you simplify is pretty much the same, depending except for the index. So I'm gonna reorganize this as r is equal to 1 to n-1. That's what we have. But in this case, we can use, starting from 0. But as you can see, r equal to 0 is really not that big of a deal, because if I put r equal to 0, it's going to be 0. So now I can re-express this as simply just 1, because if I put the r equal to 0, it's insignificant. That's great. Now my job is to simplify this. How can I simplify this? Well, we had the sum of integer square. If it was n, it was n times n plus 1 to n plus 1 over 6. But this time it's going to be n times n minus 1 to n minus 1 over 6. I'm just replacing the n with n minus 1. Not a problem. Not a problem. Okay, so then this will be replaced by the expression I have here. That's going to be my lower bound for my integral, because as you can see, the left sum for the increasing function is smaller. So that's my lower bound. So if I go back to the integral once again, I can find this inequality. And that was our job to find in this question part D. Okay, so with this inequality, what they have asked you to do is, by taking the n to infinity, they asked me to find what's going to be the limit in between. So let's try to find the limit. So I'm going to go to the right-hand side, okay? The limit here, n goes to the infinity. And what do you think the limit of this sequence? What should I do first? Do you think I'm going to attack on the numerator or denominator? Do you think I'm going to start with the numerator or denominator to simplify things? Yes, I should start with the numerator. And in fact, if you expand this, it becomes 2n cubic plus something something. And I have this. In the other terms, I don't care because that's going to be smaller degree. Now, if you divide top and bottom by n cubic, the highest power, n goes to infinity, x cubic, times 2 plus any other term will be, for example, having, it's not x cubic, x squared to n squared, will be a2 over n, a1 over n squared, constant will be n cubic over 6. But if I send n to infinity, they will all become 0. So, I will have only 2 left. So in fact, 2 over 6 is 1 over 3 x cubic. That's your right-hand side. And in fact, you can do the same thing on the left-hand side of taking the limit. If you did, we will also give you the 2n cubic as a leading term, and 6n cubic is the one in the bottom. They have the same power, so you only follow their leading coefficient. So it's also going to converge to 1 over 3 x cubic. So the left, so lower bound, upper bound, both converge to the same limit of the x cubic over 3. That means the what's in the middle must also converge to the same limit as n goes to infinity. And that's one way to prove this integration using the squeeze theorem. Okay, so this is another paper 3 problem on the other. Okay, so if you ask me what's the historical significance, AB is something called the Fourier-Habermas formula. And for E and F is sandwich theorem. Okay, let's move on to the next question, because I believe next question is going to be the one that's going to annoy the most, because we were not exposed to many of the statistical probability related paper 3 problems. So, but it's important for us to know the definition and also know the formula for expected value, variance, etc. So let's dig in. So for here, it says about the estimating parameter from the data. Okay. So they are saying that I can use this information for free. That is great. That is great. But I think they might have actually typed it wrong, because this is a misprint. This is also a question from a holder, but it should be a square. Okay, I think they did a misprinting here. Please know that it's if you have a constant coefficient for the variable, for the variance, it would come out as a square. So I think that's missing in the document. So it should be square here. So please correct. Okay, so they're saying I can use for free, no problem, right? So now let's have a look at the part A. So this type of problem will be the unseen. So that requires you to do the learning phase. So they're gonna, ask you to play around with some easier examples and then gradually develop into more advanced, which we haven't seen before. Okay, so let's have a look at the part A. They're saying the X bar, okay, is a random variable representing the sample mean of two observed values. Okay, what does that mean? Well, we have an observation of X1 and X2. Using these two, how would you define the X bar? How would you express the X bar in terms of X1 and X2, which is the observed value, according to the definition here? Yes, very good. Great answer. It's going to be X1 plus X2 over 2. We're simply just using the definition of average. Okay, that is great. So done. And now they're saying, okay, get us the, what is it? The expected value and then the variance. All right, why not? So if I take the expected value on the random variable of X bar, which we don't learn, it's only for the AI, but they don't need to prove it, but we are proving it as a paper 3 problem. Then I can put it here. And using the linearity condition for the expected value, I can take this out as an expected value of x1 over 2 plus expected value of x2 over 2. And this constant coefficient can go outside. It's going to be 1 over 2 expected value of x1 plus 1 over 2 expected value of x2. That's great. But here's the thing, they define the x1 and x2 to be the independent and identically distributed with the expected value and the variance the same thing. So what I can do is, because x1 and x2 were the independent and identically distributed random variables, it's just going to be 1 over 2 mu plus 1 over 2 mu. So that's just a mu. We call it unbiased estimate. So that's great. But now let's try to go with the variance. If I try to do the variance now here, where it's going to be pretty much the same thing, I'm going to change the variance, but please remember, for the variance, the coefficient will come out as perfect square. So we have a x1 over 2 plus x2 over 2, but the constant coefficient will come out as a perfect square. So it's going to be 1 over 4 variance of x1 plus 1 over 4 variance of x2. That is great. So, and we were given, guys, that it was identically distributed. And for the variance will be sigma square. So it's going to get double. So it's going to be 1 over 2 standard deviation square will give you the variance of sample mean, which is not the same as the initial standard deviation. Okay, that's great. So we got the B, right? So find the expression that was 1 over 4 sigma square. No problem. Okay, then let's have a look at the sample variance is defined as the following. Sample variance is defined as the following. And how would you express the expected value of x squared using the variance and expected value? For this one, is really checking whether you know the formula or not. Do you guys remember the formula of the variance using the expected value? The formula for the variance was expected value of x squared minus expected value of x perfect square. So that's great. What we can do is rearrange for the expected value of x squared. So this is what I would have, and that will be same as variance of x plus expected value of x perfect. It's just a formula. That's great. But now they're saying, why don't we do that for the E of s squared, where it was defined as the following? But of course, the question has asked us to define what the expected value of x squared was. Of course, I want to use it on here. So what I'm going to start with the left-hand side, and instead of using the x, I'm going to use s. So then it's going to be same as variance of s plus expected value of s perfect square is what I have. And then let's try to simplify. What I have here is variance of the s, where the s was, maybe it's not easy because I don't have a s. I don't want to take the square root, sorry. Okay, maybe I would not use that definition yet. Maybe I would just I would just replace the s square right away. My bad. So it's going to be expected value of just that right away. No problem. Which I can use the linearity of expected value. So it's going to be expected value of x1 squared over 2 plus x2 squared over 2 minus x bar squared, where it's going to be 1 over 2 expected value of x1 squared plus 1 over 2 expected value of x2 squared minus expected value of x bar squared. And this is by the linearity of the expected value. And it was given in the question. So we should be able to use it. What was given of this linearity property of the expected value and variance. That's great. Okay. And I think we should try to use the information that we derived before. I think the information that we derived were the expected value and variance of x bar. Okay, let's try to get back there. So we were given the expected value and variance of the x1 and x2 individually, as well as the x bar. So I want to use that. Okay, so expected value of x or mu, variance of x was sigma squared. But now I need to find expected value of x, 1 perfect square. For that, I would like to use the definition that we talked about. This was, what was it? The variance. Oops, sorry. This was a variance of x plus expected value of x perfect square. So expected value of x1 squared will also be the same as variance of x1 squared plus expected value of x perfect square, where we know the variance of x1 squared will be just, not x squared, just x. The variance of x1 will be just sigma squared. That is great. And then the expected value was simply just mu, and it's going to be mu squared. That is great. So that will be given for the first term divided by 2. And then the second term for the x2, because it was identically distributed, will be giving the same value, right? Because their expected value and sigma were the same, mu and sigma squared. So that is great. And then what will be the expected value of sample mean square? Well, we found the, expected value of the sample mean, and then the variance. I believe the expected value of sample mean was mu, and then the variance of sample mean were 1 over 4 sigma square. That was given. Okay, so with that, you can derive the expected value of sample mean square, because by the definition, it was variance of sample mean plus expected value of sample mean square. That is great. And for the variance, I have 1 over 4 sigma square for the sample mean. That is great. Sorry, was it 1 over 4 or 1 over 2? Oh, my bad. Sorry, it was a 1 over 2. Okay, my bad. It was a 1 over 2, so it was not 1 over 4. So I will change this as a 1 over 2. Okay, thank you. So it's a 1 over 2. And plus the sample mean expected value was simply the same as mu. So I have a mu square there. And that's great. So if I go back to the value that we were trying to simplify, which was this humongous, it was a e of s squared, but this time it's going to be subtracted by the expected value of a sample mean square, which is what we just got. And that is great. So if I try to simplify further, well, it got double, so it's the same, but you're just subtracting these two, where mu squared is going to cancel out, but then the variance will be halved. And that is going to be e of s squared in this case, where s squared were defined as, in the question, like this. Oh, sure, very good. We did derive the sigma square over 2. That is absolutely great. Okay. But of course, you know what? For the first time, this is going to be really complicated because we were substituting a lot of numbers back and forth. Therefore, it's important for you to try this on your own and check my note and video later. But if you just have to understand now is that this is obviously a potential paper 3 problem, but the essence of this is whether you're able to apply, whether you are able to apply the new definition or formula, okay? You already had the phase of a learning phase, and it should be extended to the proving phase. That's the important concept for the paper 3. That's the only thing that you need to understand now. Of course, you should be trying this problem on your own. I really encourage you to do. But at the moment, what you want to do is, okay, can I use that information? They ask me to do the warm-up here, and then the real exercise, can I do that? Okay, that's great. Now let's move on to part D. I want you to read it carefully and tell me how you want to do D1. Tell me your initial step. You don't have to give me a value, but tell me, oh, I will do this, do that on the D1. That's all I want to know. Just the first step. If you want to show unbiased, what we were doing in this, practice is that it must give you the same mean. What they have defined was who it will be unbiased estimator is one whose expected value equals to the population parameter. Okay, here my population parameter was mu. So what my aim here is to show is that if I take the expected value of that parameter, I expect to get mu. If I could show that is the unbiased parameter. We do not learn this in the syllabus, but it's okay because in the paper 3 on the spot, they will tell you, they will define the concept, and we need to use what's given. So what's given here is as long as I can show taking the expected value of that variable and giving us the population mean is what it means by the unbiased parameter. Let me try. So I'm going to take the expected value of m, which is expected value of 2 over 5 x1 plus 3 over 5 x2, which I can then expand it as a linearity, which will be then 2 over 5 expected value of x1 plus 3 over 5 expected value of x2. That is great. But again, the x1 and x2 were identically distributed, so it's going to give you the mu and mu also, respectively. So then it's going to be 2 over 3 plus 3 over 5, hence becoming 1 times mu. And as long as you show that, yes, taking the expected value on the variable, giving us the mu, does prove the unbiased estimator. Okay, that's good. Okay, let's have a look at number 2. When comparing two unbiased estimator, the one with lower variance is said to be more efficient. And they're saying determine whether m or the x bar is more efficient unbiased estimator of the mu. We already know the variance of x bar, I believe. The variance of x bar, we got it from the very first part of the problem. It was 1 over 2 sigma squared. That's okay. But now I'm going to take the variance of the m, which is going to be the variance of these two variables. But using the definition defined on the question, using this perfect square form of the variance, I can define this as the 4 over 25 variance of x1 plus 9 over 25 variance of x2. That is great, which is going to be 13 over 25 variance of sigma square, because they were identically distributed. They will have the same population, which is a slightly bigger than half, isn't it? So who is more efficient? Sample mean is more efficient because it's got smaller variance. Again, we do not learn such thing in our syllabus. Doesn't matter. Paper 3 can give you that, right? And I just have to answer according to the definition given by the question. That's the difficult part. That's very hard to understand. It's like go with the flow. This is go with the flow. Okay. So I determine what it means by more efficient. Smaller variance, I got it, no problem. Let's have a look at part E. It says, in a promotion, tokens are placed at a random in a box of a cereal. Y is a random variable describing the number of boxes of cereal that need to be opened, up to including the one where a token is found. 2 independent investigations were conducted. Okay, so 2 independent investigation. I smell that it's going to have 2 variables, isn't it, for the observation. But now I got the Y. Maybe I would probably have to do Y1 and Y2. As you can see, that is great. So the tokens are placed in the cereal box with the probability P proportion. Presence of a token in the cereal box is independent of the other. And find the expression of L, the probability of observing the Y1 and Y2 in terms of A, B, and P. Okay, so of course this is difficult, right? This is a difficult distribution because we do not learn this distribution. Okay, but what they're saying here is I want to have probability of Y1 is A and Y2 is B. But it's got the language of N. That means it's probably dealing with the intersection. But what's great about the intersection for the independent events? Where does it say independent? Oh yes, there you go. What's great about the independent with the intersection is that it can actually be put it into the product. So what I'm going to do is I'm going to express this as multiplication. That's great. Then what's important here, guys, is how would you define your distribution? Because from reading the context of the problem, you do not, let me repeat, you do not learn such distribution. we only learn binomial and normal distribution. In the context of problem, you do not learn it. Doesn't matter. We should be able to derive it from the mathematical approach. I want you to read carefully. Binomial distribution, all right, is to see how many success I have from a fixed number of trials. That's a binomial distribution. But here, the random variable y is defined as what? I need to open many boxes to find how many success. How many success am I aiming at is the question. On the underlined sentence, how many success do I want? I want you guys to tell me. Please tell me how many success do you think I want in the underlined context? 모지. Yes, very good. Here, you just want one success. Okay. Out of how many trials? If I say probability of y1 is A, okay, what it says is the following. My first success appears in 8th attempt is what it means in the context. And it's not easy to tell, you see, because it doesn't tell you, it doesn't feed you that. It says, I want to find one token that is successful after trying y many. In this case, if I say y equal to a many, that means, all right, first a minus 1 many trials, you had failure. Where we're going to say failure is a 1 minus p, and each trial, my friend, is independent. That means I'm going to multiply this many, many times. How many times? The number of times I had failure, which is a minus 1 many times. But in the 8th time, I had my first success. And what you see here is called a geometric distribution. And again, it's not in the syllabus, but it can be on paper 3. And in fact, you know what? This really confirms my claim. What I mean by that is in order to, okay, prepare for your paper 3 right now is to be exposed as many as unseen problems on a textbook. This geometric distribution was seen in May 2024. Okay, let me show you. So geometric distribution is not in our syllabus. Let me repeat, but it was in the paper 3. There you go. But what's challenging here? They don't tell you that it's a geometric distribution, right? They don't tell you how to build up the distribution. We got to build it. This is a May 2024, paper 3, and this is your geometric distribution. And another popular distributions will be potential exam questions will be, you know, negative binomial or Poisson distribution. Those are the potential paper 3 problem regarding with the statistics. But anyways, so being able to build that is super important. So now I go back here because I got a sign for the B also, right? So that means I tried B many times, B minus 1 many times, I failed, but Bth time I had my first success, right? It's very hard to put in words, isn't it? But if I now try this geometric distribution here, and for the second one, it will be just replacing the A with B because that's the number of trials. No problem. That, my friend, is your expression of the distribution. And then the question says, if so I've got the E1, and it says find the value P which maximize the A. Okay, now it's talking about the maximum, right? And unfortunately, okay, I cannot use calculator. Why not? Because at the moment, I have too many unknown parameters. If you want to put in the calculator, it needs to be given one variable. There are too many parameters here. There are P, A, and B. I cannot use calculator. For this one, you have to differentiate on your own. So here I'm looking for P. So P is going to be your unknown variable. But maybe, of course, I'll try to put together. It's going to be 1 minus P to the power of A plus B minus 2 by using the property of exponent. I have a P square here. Then I'm going to differentiate. So this is L function in terms of P. So I'm going to do DL over DP, which I'm going to use a product rule. Okay, let's try. It's going to be, if I differentiate this first, it's going to be A plus B minus 2 times 1 minus P to the power of A plus B minus 3 times negative 1 using the chain rule. But you got to multiply by the P squared by the product rule plus first term remains the same. But then I'm going to multiply by the derivative of a second term, which is going to be 2P. But of course, you're not going to expand, but rather please factorize. And the common factor that I see are, first of all, P. And then the another common factor that I can see will be to the power of -3. So it's going to be 1 minus p to the power of a plus b minus 3. That's my common factor. So let's try to factorize. So I have a negative p times a plus b minus 2. Okay. And then the next one is going to be 2 times 1 minus p. Okay. Then let's try to please simplify further within the bracket. So it's going to be minus AP minus BP plus 2P plus 2 minus 2P. Okay, that's great. So I can cancel out the 2P. That's nice. Then I have 2 minus A plus B times P, right? So that's my first derivative. And the reason I found my first derivative is because, we were looking for the maximum. That means you should try to find the stationary point first. But of course, P were defined to be between 0 and 1. So neither of these two terms cannot be 0. That means your third term must be 0. This suggests P is equal to 2 over A plus B. But what you just did, guys, okay, what you just did is only, all right, is only stationary point. You have to verify whether it's going to be maximum or minimum. And for that, you can do two things. Either you do the sign diagram or the second derivative test. But of course, for me, I will do the sign diagram because I don't want to differentiate this once again. It's going to be crazy product rule because there are 3 terms here. I don't want that. So let's do the sign diagram here. So maybe I can come up with for the sign diagram, what you got to do is you got to try the ones in the neighborhood. So maybe I would put 1.9 over A plus B and then 2.1 over A plus B, right? Why not? So if I put, for example, 1.9 over A plus B, that's going to make it positive. That's going to make it positive because 1 minus P, whatever the probability is, it's going to be positive. So it's insignificant. These two are insignificant. Oh, well, in that case, hold on a sec. I know P is between 0 and 1. So I know these two terms are insignificant because it's always positive, no matter what. So only thing that I have to check is this term, which is going to be a linear in terms of P, and it's got the negative gradient. It's going to be decreasing. And then the signs are changing from positive and negative. Aha, that means my original function would have the increasing to decreasing behavior. So I do know I'm going to have local maximum at 2 over A plus B. You have to verify the nature of stationary point. Just because the derivative is 0, you cannot say it is going to be maximum or minimum. Okay, that's great. So that was a number 2. And it says in the first observation, y was found to be 4. Okay, so that's y1, isn't it? I had the y1 is to be 4. And the second observation, y2, is 8. Find the unbiased estimator for the variance of y, they say. Okay, hold on. Find the unbiased estimate for the variance of y. Well, we do not learn the unbiased estimator for the variance, but in the question, they have given you, right? They have given you. So what you want to do is to see whether you can use that definition. We were given, right, that the what are we given? Unbiased estimator for the population parameters is the whose expected value equals to the population parameter. Right. So if you want the unbiased estimator for the variance of y, what do we have to do? Where y1 was 4 and y2 was 8. Let's think. We had sample variance to be the following. We had the sample variance. In AI, you learn the sample variance is the unbiased estimator. But have we proven that this is unbiased estimator for the variance? Oh, we did. Yes. E of s squared is this. But that's not okay because I believe I need to have E of s squared should be sigma squared to be called unbiased. Okay, so let's check this out. So I want to use this because they have given me the definition that, okay? So what the definition here is, if you want to call the unbiased parameter, you put something and it would give you, so for example, if I give you sample mean, you need to get population mean. Then this is unbiased estimator for the mean, is what the question has given us. That's the definition. So if I want unbiased estimator for the variance, I want expected value of that A population should give me sigma square is what we want to do. And now for the sample variance is defined as such, but we saw expected value of S square was 1 over 2 sigma square. And that's not cool because I'm supposed to have population variance. So let me check back actually. X1, I mean, it was a 1 over 2, I believe, right? So you gotta multiply by 2, I believe. You should multiply by 2 because I want to get sigma square. So I want expected value of 2 expected value S square will give me the sigma. So by using the property of expected value, these two can go inside. I want this. I want this. I think there could have been a typo in the textbook. Let me double check later. But I think it should give you the variance square because that's the population parameter. In that case, what I want you to do is use a definition. But this time, I had my observation y1 and y2, where it was 4 and 8. So what we can do here is S square will be the y1 square plus y2 square over 2 minus y bar square, where it's going to be then 16, 64 over 2. And then y bar square will be the average of these two. So you add them, which is a 12, divided by 2 is a 6. So you're going to 6 square. Okay. Then I got 80, and that's a 40 minus 36. It's which is going to be 4. Okay. But as we said, I want to get unbiased parameter. That means I need to get sigma square. So I got to multiply this by 2. Okay. So I will do expected value of 2 times 4, which will get 8, right? Because expected value of a constant is constant. Okay. So unbiased estimator for the variance of y will be 8, according to the definition on the textbook. And then also the maximum likelihood of the estimate for P, where P was defined to be A plus B, and now we just had A was 4 and B was 8. You can put 2 over A plus B was the maximum likelihood. So 2 over 4 plus 8, which is 1 over 6, is going to be the maximum likelihood estimate for P. And as you can see, yes, super challenging to follow. And only reason this is challenging is because we are not used to it. This is one of the unseen problems, of course. But imagine that I try this problem, okay? Imagine I try this problem in 2024 April, okay? Imagine I try this problem in 2024 April. Then in 2024 May, I would have aced this question because it's talking about the geometric distribution. It's talking about the expected value. It's talking about the variance, okay? And it's talking about the efficiency here also, actually. This is crazy, isn't it? In fact, the entire problem was photocopied from a question from a textbook. And that's what you need to do now. You need to expose more problems from the textbook. There are a huge number of questions on the paper 3 from the textbook that was not seen before. And I intend to go over them more, but I will take a pause now, okay? And I will probably resume again in the evening time in Korea so that I can finish these questions, all the questions of paper 3 from many textbooks. What we have accomplished today is that we went over the paper 3 problem from the Oxford, binomial coefficient, Pascal's triangle, using the calculator to describe the parametric form, Hanoi Tower, and then the hyperbolic function and its integration using trig substitution, beautiful question, and the Fibonacci sequence, Far-Haber's formula, and then this beautiful statistic problem. So let's try to go over more questions. I believe now the haze is left for the paper 3, and then I will go over that today's later evening. But that's pretty much it for me today. Thank you for joining. I will send you the note and the video, so please revise until the Wednesday. That's for me today. See you around. Thank you.